tell you a little bit about. So, brief outline. So first, I'll briefly review the basic concept of optical sampling, and really there are two type of schemes I'm going to talk about, and one is asynchronous optical sampling, and this is other work that we actually did, but it has a lot of similarities. It's a fairly well established technique. So I'm going to start with that, and then I'm going to talk about the technique that we actually spent some time studying, and is the optical sampling by cavity tuning, and specifically I'll mention three potential applications, and in the end I'll just briefly tell you, if time permits, a little bit about our group and what we can do here. So optical sampling really is a technique that is used for detecting very, very fast optical signals. So if you think about one optical signal, for example, like the optical communication pulses, becomes shorter than 10 picoseconds, in the order of 10 picoseconds. Really, there's no electronic that you can actually use to, or cost effectively use to detect that. Just simply the electronics that don't have that bandwidth. So one way to probe these optical signals is to use optical sampling. What optical sampling does is a lot like the electronic sampling, like the sampling oscilloscope. Basically, you set up for example, this is quasi-periodical optical signal, these pulses. Then what you do is you somehow create these gate signals, very short gate signals. And these gate signals, you don't have to really probe the profile of each pulse, but over many periods, you see these gate signals, they sort of map out the overall envelope of these optical signals. So for each one, you only need a slow detector. Okay, so although the slow detector cannot really probe the shape of this optical signal within this gate, the amplitude nevertheless represents it's proportional to the amplitude at this point. So if you then use a slow detector to collectively probe the over many periods, okay, overall you get something like a eye diagram that I'm sure a lot of you are familiar with. Okay, so this is just a basic concept of optical sampling. So you see of course the key is how you create these very short gate signals. And so there are different ways to do that. The most straightforward way is to use the nonlinear effect. So for example, you have a nonlinear material here. It can be a crystal, it can be optical fiber, whatever. And typically use a third order nonlinear effect. So you have your ultra short, you have to have your very short optical pulses to create the gate. Okay? And this is your optical waveform that you want to try to probe. And then you have them both go into your nonlinear medium, of course, because the nonlinear effect depends on both signals. So of course, what you get out of that is gated by your ultra short pulse signal. So that way, you use a slow detector and probe the very fast optical waveform. There are other ways. The problem with this is, of course, your signal has to be strong enough in order to create a reasonable amount of nonlinear effect. Okay, so because of that, people also figure out a linear optical sampling. So that way, you don't have to use nonlinear detect. You still have an optical wave, you still have your optical pulse, but you can create a relatively complex array of detectors, with some phase shift. There's a theory about that. I don't want to get into details. Typically, it's called a dual quadrature detector system. So you basically use two balanced detectors, and then we have a high phase shift, and you play with those and use a linear, just simply linear interference signal, and you can still figure out what the optical waveform is. Okay. Now, there's a special case which we're going to focus on. That case is when your waveform turns out to be a periodical, very periodical, regular pulse train. Okay? So when your waveform, the one that you're trying to detect, is a periodical waveform, like from a femtosecond laser, and you can use a second femtosecond laser to actually probe this first one. Okay? And it turns out to be a very, very easy. You don't need those. You don't need a nonlinear effect. You can use a nonlinear effect. You can actually use both nonlinear or linear effect. It doesn't matter. The key thing here is you just need to have the pulse train, overlap. Okay? And you shine on the detector. It can be a nonlinear detector. It can be a linear detector. It doesn't matter. But what you do is you want to have these pulses walked across each other. Okay? And so what you do is you offset the pulse, the pulsing rate, the repetition rate of the pulses, okay, by a small amount. So when you have these two pulse trains propagating and hit the detector, depending on the temporal location, you can see these two pulse trains slowly walk up each other. So what you actually detect is a slow periodical signal on the detector, which actually map out in essence, it's just a cross correlation between these two pulse trains. Okay. Now, since these pulses are all periodical, the cross correlation is basically you can retreat back to your original signal. Now, from a frequency domain point of view, you see each pulse train in the time domain basically corresponds to a cone structure in the frequency domain, right? Everybody understand. Fourier transform, okay, periodical waveform give you another cone in the frequency domain. But because of the repetition rate offset, you see the cone spacing between this laser and this laser is slightly different. So the frequency domain, assuming these are two identical lasers, except their repetition rate are different, and you can see this red spectrum and this green spectrum, they're pretty much identical, except their cone lines are slightly different. Okay? So when you have these two cones beating each other on the detector, okay, what you get is another cone, basically a replica of these two spectra, but down convert to the frequency difference between these cone lines. So you basically down convert that into a RF, into the RF frequency domain. So this is optical frequency domain, okay, 10 to the 14 to 15 hertz. Now this is RF, it's like a gigahertz, megahertz. Okay? So you down convert that here. So immediately now you can see the potential application of this in spectroscopy, because you basically down convert whatever here typically hard to probe into the radio frequency. And if you think about this technique, it essentially is, for all the optics people here, it essentially is another way of doing, using a scanning interferometer. So if you think about this is, for example, like one of the femtosecond laser, okay? You don't have to do, it doesn't have to be frequency comb, but in this case it's frequency comb, okay? So it's a femtosecond laser with this regular, very regulated pulse train coming out, okay? You're going through whatever you want to detect, okay? And going to this simple micro interferometer setup, okay, where you have this two arms, one arm is scanning. And you see, basically what you do is, while you're scanning, you're scanning this arm, you're creating this, as a detector, the pulse train from this arm and the pulse train from this arm basically just walk off, across each other, back and forth. It's just like, creating a cross-correlation signal. And then you can do all kind of analysis, whether like a Fourier transform of that cross-correlation, and you just get the spectrum. So what you're doing here is exactly similar to what happens here. The only difference is here you have to rely on a mechanical scanning, which is very slow. But here, because of the there's nothing moving, okay? No moving part, no mechanical part. It's just because of the offset of the rep rate, and so this can be very, very fast. So that's the main draw of this technique. They can create very fast scanning, and up to, typically the scan rate is the frequency difference between these two repetition rates, and it can be as high as megahertz level. So you're talking about, basically you're talking about this scheme with something moving at megahertz frequency. So that's the main advantage of this technique. So it is called asynchronous optical sampling. I mean, if you look up the literature, basically there are different in different fields, people call asynchronous optical sampling, with somewhat different meaning. But in our case, in the ultrafast field, when we are talking about asynchronous optical sampling or ASOPS, basically we're referring to this scheme. So I just want to make that clear. Okay, so just elaborate a little more on the advantage of ASOPS. When you think about the typical interferometer, whatever the form of the interferometer, you have to have some kind of scanning, and the conventional way is, of course, this linear translation stage, motorized translation stage, that typically just give you hertz level scanning, 100 hertz. That's probably as fast as it can go. Okay, and you can go up to kilohertz level with these spinning mirrors or spinning polygons. But again, that's probably as fast as you can go. And also, the drawback of these techniques is, first, you create vibration, and second, the scanning depth is inversely proportional to the speed. The higher the speed you go, the smaller scan depth you can go. Right? So, for example, if you turn this one up to like multi-kilohertz level, you basically just have a 1 to 2 millimeter depth. There's no way you can go bigger depth, bigger range, okay, with a mechanical system. So that really just highlights the advantage of using this ASOPS technique. So, basically, to just show you some of the examples, I just grabbed some of these references out of the internet. And we didn't do work here, but I thought it could be interesting. And for example, like this is a work based on this ASOPS idea, and this is spectroscopy. Okay, and in this frequency range, and you can see over like a few seconds they can collect, I don't know how many, hundreds or thousands of these spectrum. Okay, so this is a spectrum with the time, and you see they basically, these are from this very narrow sort of time range. You can see that basically you can look at these spectrum over time. You can basically see the spectral evolution over time with very fine temporal resolution. So that just gives you another dimension. So typically, conventionally when you look at spectrum, that thing has to be stationary, a system. Okay, there's no way, because of the taking the spectrum, take some time. You cannot capture the dynamics of the spectrum change. So here they just show that with this ASOPS, you can really make the spectral measurement very, very fast. And this is another, it's called a time resolved spectroscopy. Now here, I think they were studying some dynamic effect in the semiconductor devices. So basically, they introduce an impulse into the semiconductor device, and they probe the how they respond. Follows the time. So this is the impulse, okay, and then the time 0, and then you probe the response of the system, based on time. Okay, so then what they can do is they zoom in part of that. They can detect these very fine oscillations, and then you do Fourier transform of these oscillations. You can see the features, and so you can derive some properties of the device based on these measurements. Now these are some other applications of ASOPS. For example, you can do tomographic imaging. Okay, and so this is a system. It's basically 2 lasers. Okay, and this is your sample. And essentially, so the tomographic imaging, and we'll talk about that a little detail later. It's basically just you probe the response from the it's like a reflectometry, right? The reflection of your target. Different layers will reflect the signal coming in at a different time. So all you need to do is just to have a time resolved magnet to detect this signal for different time. Okay, and the old way to do that is just to use a scanning stage. But with the ASOPS, you can do this with very, very fast rate. I think they demonstrated up to like tens of kilohertz. You can do the scan rate. And so here they demonstrated, for example, like this is a human nail, fingernail. You can see the this is a vertical scale, so over 2 millimeter range, and you can actually see the cross-sectional structure of your nail. And I think this is just a typical Scotch roller, Scotch tape. And so I think they basically want to demonstrate how deep this technique can give you. This is in the order of a centimeter. And you zoom in, you can see this layer structures. Okay. And this is another work. This is they use the ASOPS method to do long distance ranging this is work done by NIST, and so what they are trying to do is to create a method that can be used, potentially can be used to lock up the distance between satellites. So eventually, in the future, they want to have this satellite formation, so that you have a space-based telescope system that you can span millions of miles, and they all the signal they receive can be coherently combined. So for that, you have to have very precisely locked spacing between these satellites. So, and over very long distance. And the problem with the conventional method is, of course, you use interferometric method. You can log you can measure the distance with very sub-wavelength resolution. But the problem is, over long distance, you have the problem of ambiguity, because these wavelengths, they repeat every wavelength. So over long distance, how can you discriminate, this? So there are different ways to do that. And the nice thing about using the femtosecond laser is you can combine the time of flight method with this pulses. Okay, you can basically send a pulse, you measure the timing of the pulse arrival time, and that will allow you to measure very long distance. And on the other hand, you can interfere these pulses, okay, and create an interference method that will allow you to reach very high resolution. So the selling point of this technique is that you can basically measure very long distances. Well, I think in this case it's tens of meters, and with sub-wavelength. I think they forgot exactly how accurate they claim it is, but it's well less than wavelength. Okay, and so they use exactly the ASOPS technique. There are two frequency cones coming in, and one goes through what you're trying to measure, and then the other one here works as a reference. And you combine them, you put on the detector, you analyze the signal. So that's another application. Okay, so so much about this ASOPS. So it's very nice, very elegant technique, and it has become very popular these days. In a lot of in the field, actually there are commercial ASOPS systems on the market. But one key drawback for ASOPS is you have to have two frequency cone lasers, two femtosecond lasers, and in a lot of cases, especially when you need to do this high precision spectroscopy, you have to phase lock these two lasers. And that involves a lot of expertise, a lot of complexity, and a lot of cost. So the question we were asking ourselves a few years ago was, can we do something similar to ASOPS, but with only one femtosecond? We don't want to have the second. Okay, so that's what these optical sampling by cavity tuning is about. So here I show a basic structure of a ultrafast laser. It's just two mirrors, sort of a laser cavity. You have a gain medium, which is pumped, and so you have a laser here. You add a modulation here, and that gives you mode locking. Mode locking creates short pulses. So altogether, this is your ultrafast laser. Okay. So what we do is we add a modulator on one of the mirrors, and this typically is a piezo electric modulator. Okay. And so we modulate this PZT, and that would modulate the position of this mirror. So when the mirror is modulated, typically the modulation frequency can range from tens of hertz to kilohertz, up to basically the bandwidth of this PZT setup. Okay, when you modulate this, you change the cavity length. When you change the cavity length, you change the pulsing rate, because the pulsing rate depends on the cavity length. Okay, and so you're changing the repetition rate of these pulses coming out of the laser. And so how would that create the delay scanning? Well, we put the output into an interferometer, okay? And this interferometer will make this interferometer highly mismatched in terms of their path length. So this is you can think about this as it doesn't matter, it's a Michelson or Mach-Zehnder, is you have pulse coming out, the split here, and one goes through a short arm, the other goes through a long arm. Okay? And so the arm length is mismatched. And so then you monitor the arrival time, pulse arrival time at your target. Okay, from this short train, pulse train, this short arm, and from this long arm. And you find that when you change the repetition rate, when the repetition rate is different, okay? This pulse arrival time are different. And if you're modulating this, you're modulating the arrival time difference. That way, you create a pulse arrival time scanning, a delay scanning. And you only need one laser. All you need to do is to somehow figure out how to construct a highly mismatched or imbalanced interferometer. So we did some theoretical analysis, even some numerical simulation, and these are unimportant. The important thing here is this relation. Now this is the effective pulse delay, maximum pulse delay that you can create at your target. So this is the one that you want to create. How much delay scan you can create with. That's the number. Okay? You see, it depends. It's proportional to the cavity length detuning. In other words, the amplitude of the cavity length modulation. Okay? And there's a factor in front of it. This factor depends on the ratio between the interferometer impedance and the nominal length of the cavity, laser cavity. Okay? So here's the nice part. Typically, for a PZT modulation, this detuning, maximum is about a few micron, 10 micron. That's about what you can get out of a PZT. Okay? But this ratio, okay, from it imbalance, if you use a fiber as a fiber loop as a part of the interferometer, you can really make this one very long, in the order of kilometer. Okay? But the cavity length is typically in the order of 0.1 meter to 1 meter. So you see, this is a big ratio. This ratio can be 10 to the third, 10 to the fourth. Okay? And you see, with a very, very small PZT modulation, you can create a very large detuning or delay scan in the order of centimeter or tenths of centimeter. Okay? So that's the sweet part. So you see that even though the cavity tuning, you still use PZT, essentially you still use a mechanical system. Okay? But you only need to tune with a very, very small amplitude. that would allow you to increase the bandwidth of the tuning, because you don't need to tune millimeter or centimeter. You only need to tune micron level. Okay, so the PCT typically can give you bandwidth tens of kilohertz, even 100, 200 kilohertz are already demonstrated. So with that small detuning and with this very large ratio, you can create a very large effective pulse delay. So that's the nice thing about this OSCAT. So with that, so we constructed a experimental demonstration for our idea. So what we do here is we use our femtosecond laser to modulate its cavity length, and we set up a highly imbalanced interferometer. So here we use optical fiber. Single mode fiber is over 1 kilometer. Of course, and there's one issue you have to address, because when ultra-short pulse going through a fiber link, pulse will be broadened. Okay? If you have a broadened pulse at the output, then the temporal resolution will be very low. The signal, average signal will be very low, so your signal noise ratio is very poor. So what we do is we have to compensate the dispersion. So I have to put in a dispersion compensating fiber. So here we only use just a simple dispersion compensating fiber, nothing fancy. Okay, and then so that arm goes to shoot on a target. So here we have a target, and target reflects the pulse, and then goes here, and this is a short arm. Okay, this is a short arm. This whole thing is a long arm. So the two pulse trains combine here, and you put a detector, and then you analyze them. Okay. So we did some, detailed work on how to optimize these pulses. Eventually, we get these pulses below, I think, 400 femtosecond, 300 femtosecond range. Okay, and then the cross correlation from these two pulse trains give us, I think, 700 femtosecond with that maximum. So with that, we demonstrate a target tracking system. Like I put it here, so we have a target here. We put a target on a moving stage, and for a speaker, and we find that the system can very nicely track the displacement of the target from its nominal location. You can see this displacement and the signal, the cross correlation signal is very well representing the displacement of the target. And then what we really want to see is, okay, how this system, because everything is about speed. So we want to see how our system can actually monitor the quick movement of the target. So here, so that's why we put a speaker there. So then we modulate the speaker and let the target, shake back and forth at 50 hertz, for example. And we find that the system can very nicely track the 50 hertz movement of the target. Now, in order to make sure that this 50 hertz movement is actually from the movement of the target, not from something else, we actually would use a second laser and shoot on the system, and use a second way to monitor the movement of the target, and we find that these two, the green one I believe is the second method, the red one is the And of course, we also want to know the actual distance of the target. Okay, so for that, we did some more detailed work. We have to involve moving this mirror using an internal stage. And essentially, I don't want to go into the details, but it's very convenient. It's a very simple relation here. You just make a quick measurement and you can figure out the absolute distance. Now here we convert all the distance into free space because remember the target actually is separated from the source by fiber, 1 point something kilometer fiber. So if we convert everything into free space, we find that it's about 2 kilometers. And we also compare that with what we actually measured with the fiber. We actually measured the fiber. Well, we didn't really measure the fiber because 1 point some kilometer fiber, we don't have the way to precisely measure it. But we got it from the vendor. Okay, we know that. Okay, we assume okay that's correct. Okay, so anyway, it was fairly close in the end. So okay, now about another application. So just a few months after we published our paper, there's another group in Canada. Okay, they did the work somewhat similar from what we did, but it's a very nice application. So what they do is they use this OSCAT method to monitor the vibration of a wall, and so that you can remotely detect human voice. Okay, so the human voice recovery. So you basically you can monitor very small vibration on a wall. Of course, I think their wall is not really this kind of wall. I think they use some polyester or something constructed wall. But anyway, so you can recover the somebody talking behind the wall. And the nice thing about that is they can put some high reflective, for example, like a glass, okay, in front of the wall, and which actually reflect a lot of the optical signal, but they can discriminate in their system. So they call it range result. They can actually pinpoint, okay, in the reflected signal. They only grab the signal that reflected in the, at the right time, that they know they're reflected from the wall, not from the glass. Okay, so basically you can extract the useful signal out of a very big noisy background. Okay, so here I just copied their recovered voice signal, and here you see this is the blue one is the signal reflected from the glass that's sitting in front of the wall. The green one is the recovered voice from the wall. And you see these two signals, the glass reflected signal is way bigger than the voice signal, but they can still discriminate these two and to pick out the one we want. Okay, so we also explored another application for the OSCAT system. That is, instead of measuring a target located very far, we actually measure something that's very close. Okay, and here we're basically trying to measure the layers of the sample, and that's the basic idea of the optical coherence tomography. Okay, so we have a basically similar system as the previous one, but now we focus our pulse onto the sample. So what happened is you can see this pulse pulse train coming into your sample, and the different layers of the sample reflect the pulse at different time. So all you need to do is just figure out, okay, so how much time, how much power you get from this time to time to time, and you do a transverse scan or two transverse scans, and you can basically map out the structure, the cross-sectional structure of the sample. So this is in our lab. This is our frequency foam laser, and this is the where we had our setup. We used to study, just like the previous paper, a Scotch tape. But we have a much better result than that. So here I want to show you the OCT, optical tomography measurement. For example, like a stack of glass plates. So that's the first thing we tried because we thought that's probably the easiest. Okay, so so at any one point, you basically have a stack there. You shoot your beam down to the stack, and you probe, you do the pulse, you do your OSCAT scanning, and to each scan, you basically scan these pulses across each other, and you can map out we call it axial scan or A scan, okay, at one particular location, okay, and you can see this periodical signals, and this is when the happens at the interfaces between these glass plates, okay, and now if you add a transverse scan, you move the glass plate across the laser beam. You do this vertical scan while you're doing the transverse scan, and you basically just collect a bunch of these, and you put them together, and you can reconstruct this OCT, the two-dimensional image, and that just shows you these glass plates. These the bright lines represent the interfaces between these glasses, and the edges of these glasses. Now, we for this set of data, we were not very good at this signal processing. There's a lot of signal processing involved, and we really learned a lot here. But when we first did that, we're not so good at that. So you can see these wiggles. Okay, now these are the things that due to the instability from the laser repetition rate. The laser repetition rate is not very stable. Okay, but nonetheless, it overall it gives you the picture. It does reflect the structure of the glass stack. And so here we also tried another simple system where we have a multi-phase. Okay, we have air, we have oil, we have water. And then we want to see, okay, we can actually see the interfaces. And so here you can clearly see the air, oil, the oil, water interfaces. So then we go to a more complex system. So here we use our imaging system to scan the packing bubble foam. Okay, so you just see those foam that we put into boxes for shipping. Okay, and so we put the foam onto a glass plate, and we do the scan, and this is across several, about 2 centimeters actually, and with a depth of a few millimeters. And you can see that, so this line is the glass plate, and the foam is sitting above the glass plate. There's a small air gap here, and you can see the structure of the foam. These yellow dotted lines are the guiding lines. These are artificial because the vertical walls of this foam don't give us a signal. So there's no signal here. So we just basically add these guidelines. so that you can kind of picture the shape of the foam. And these curves are the top layer of the foam. You can see it's very curvy. And especially, there's a double layer structure at the bottom of the foam with a gap in the order of 100 microns. So it's very well resolved by our image. And recently we actually tried something, because one of the applications we envision this can be used is the industrial process control. Okay? So we want to see if our system can actually work in this multi-phase system. So here we create a multi-phase system where we have put it in in container some hand soap. Okay, this hand soap, when you buy them, they have a lot of bubbles in there, trapped in there. So we use our system to scan across it. And so here you see this is the bottom plate of our container, and from here to here is the liquid, the hand soap. And up here is air. So this is the surface of the hand soap. Okay, and these are the points, are the reflecting points where we collect the signal. Okay, and these are apparently caused by the air bubbles. Okay, now this is a two-dimensional. What we can also do is we can scan X and Y. So that would create a three-dimensional picture. So that's what we have here. So here I basically just draw this model where we have these bubbles. Okay, and so you can see we have out of this 3 millimeter by 5 millimeter range. We do this scanning, and we can identify these reflected points. We kind of reflected how these bubbles are distributed. And using a similar idea, we can also find out the surface profile of a target. Okay, and now this just shows some data and how we actually progressively refine our data from this one A scan, one-dimensional, into this waterfall, two-dimensional, and eventually we can recover the shape of this. This is actually a UAH keychain. This is non-contact. We have lasers about a few centimeters above the target, and we just do these two-dimensional scans, and so then eventually reconstruct the surface of the target. So let's quickly summarize. I talked about the basic idea of optical sampling, and talk about the advantage of ASOPS, very quick scanning, very large depths at the same time, and talk about why we want to develop this OSCAT. Basically, we want to address the key drawback for ASOPS. That we want to use just a single laser. Okay, and it's a future work. We want to further develop application in spectroscopy, especially a depth result in spectroscopy, and we're now in collaboration with we're trying to set up collaboration with UAB, and when they have this beta IR laser systems that hopefully can allow us to do this, extend our application into the beta IR range. This is just a quick outline of kind of a research we're doing now, what I talk about is belongs to this here. Now we have some other research going on here. I'm short of time, so I just skip this. And also, what kind of a capability we have here? We're currently operating 4 labs here, all in the second floor of Optics Building. So, so here is the, for example, like 219. Now here we have our first femtosecond laser here, and we're right now having some spectroscopy work going on here. We actually have a system, very complicated system that we constructed for the work for free space clock transfer research. And the frequency foam laser that I was talking about is in the 207. Here is the laser, is what we got with the NSF MRI grant. And recently we set up a titanium sapphire femtosecond laser system here in 211. Now this laser is able to generate about 6 to 8 femtosecond pulses, really very short pulses. And this is what we're going to use to study very fast coherent effect in semiconductor nanoparticles. So of course, the most important part for group is the manpower, the people. So we currently have 5 graduate students, and we have several graduates here, visiting scholars, and a lot of undergrad students. I just don't have enough room to have all of them here, but we have a lot of undergrad students involved as well. So thank you for your attention. Yes.
It seems to me I missed it, but I'm not sure. How fast you oscillate the mirror. My understanding is sapphire resonator, right?
No, actually our laser is a fiber laser.
Fiber laser?
Fiber.
Okay. My concern is the mode walker, okay? Because the mode walking has to operate when the cavity is stable.
That's right.
Okay?
That's
and
right.
now you're changing the length of the cavity. So you have a total chaos in your cavity because longitudinal modes have different frequencies. So the question is, apparently you have it, so it does exist. So my question is, what is the fastest rate at which repetition? What is the highest frequency at which you can change your PCT?
That's right. Yeah. I mean that's a good question. It is actually a concern. Our fiber laser operates at 250 megahertz. 250 megahertz rep rate. Okay, so the fastest we have done is 1 kilohertz.
1 kilohertz.
Yeah, 1 kilohertz. We did not our laser. The PCT actually has bandwidth, I believe, in the order of 10 kilohertz, 20 kilohertz. But we didn't modulate that high because the engineer from the laser company said you don't want to operate that PCT too high. Because we don't want to damage our laser. But there are people who actually already demonstrated intracavity PCT modulation over 100 kilohertz. Yeah. Of course, in order to operate that high, you have to have a cavity short. The overall cavity has to be short, so that your rep rate.
But your mode blocking mechanism is a passive mechanism, right? So it's basically solid to an equator.
That's right.
That means
Exactly.
you have to have enough time.
Exactly.
To build
that
up
that is a
work.
limit. Eventually, that will be another limitation for you have a PDT bandwidth. You have the as you modulate higher and higher, your pulse quality could reduce.
Okay.
Would degrade.
We'll just describe.
Exactly.
Right. Okay.
So eventually, you just have to see how fast it works.
But at least for 1 kilohertz, you.
1 kilohertz.
Okay. All right.
Yeah.
We're interested in, I'm Dr. Fork, I'm the engineering part of electrical engineering. We're interested in, at the moment, in asteroid redirection, as well as distribution of laser power in space. The best paper I've seen for what we'd like to do, we'd like to have a spacecraft that's separate from an asteroid. And we want to map the surface of the asteroid from the spacecraft. And the best numbers that I've seen are from the NIST people. Mr. Baumann at NIST earlier this year did a paper where that her distance she could work at was about 10 meters.
Okay.
And her ability to measure points she measured, and they were working in atmosphere because it was here on Earth.
Okay.
But they were good to 10 microns. In space, where we don't have the fluctuations from air, we think we could get down closer to a micron at 10 meters distance.
Okay.
Can you say anything about what you see coming, what you're doing, what we would like to get is something similar to what the NIST people are doing. But the standard right now is 10 meters working distance, 2,000 points per second, and a resolution of 3 microns.
Okay. Well, it seems that I think it sounds to me this is absolutely doable. I mean, you just need a few microns.
The NIST people said, they gave their best data, and their upper limit for them was 10 meters.
Okay.
But that was the first time they really tried seriously to get measurements.
Yeah. So what is what is the limiting? What is the limiting their upper limit, and what is the limiting their actual resolution or precision?
It's the fluctuations in the air.
Okay.
Yeah.
Okay.
This is the worst problem.
All
So
right.
for us in space, that won't be the limitation.
That won't be the limitation. Yeah.
And we'd like to be able to, we figure we could work at a distance from an asteroid as much as 50 meters.
Okay.
We still have to be fairly close, but we'd like to work at that longer distance. And I would suspect, since that particular paper was the first time they really tried this measurement, and they used 2 different lasers, 2 different frequency lasers.
That's right. Yeah.
But I recommend that for grad students. It's a very well-written paper, Esther Baumann. I'll give the reference to anybody who wants it.
Okay.
But that's a great paper. I think it's a good direction. I think it's good that this work is going on here at UAH, and this is sort of the future.
Yep.
So we hope to be working in this area more to do with asteroid redirection in space, but similar work. So we hope to communicate with you about these topics.
Yeah, absolutely. I mean, that's an interesting topic. I just really have to see, because when you consider this laser shooting on an asteroid, then you were talking about in those demonstrations, whether the NIST that we're talking about or our demonstration, we use mirror. So that's the reflective surface. I mean,
They could do scattering. They could
really scattering.
Yeah, they could create they could take a flower and create a good 3D image of the flower.
Yeah.
In high resolution. So all they need is the scattered light. They don't need a reflecting.
Then absolutely. Then we just have to have the high quality detecting system.
Well, the thing I'm interested in at the moment, I would like to do something like what the NIST people are doing. they used 2 lasers, but they were 2 fiber lasers.
Okay, yeah.
So I'm interested
we
in
can try one laser.
One laser.
Yeah, yeah.
Because we're at the university.
Absolutely, yeah. We can definitely try. That would be an interesting topic. Yeah.
So anyway, we're eager to talk to you.
Okay.
And it's not only about 2 lasers, it's about phase locking them, which is.
Oh yeah, yeah. That was the reason I was sitting in. I remember I was sitting in the
People
conference.
did not have difficulty, in locking them. What they're doing is they're using an atomic clock.
Yeah. Just talking about what they were
This is
doing.
much cheaper.
I mean, I remember, I thought about this OSCAT idea when I in a conference. I was sitting there. I was listening to a talk from Germany, the talk from NIST, the talk from Colorado. They're all talking about this dual cone stuff.
Yes,
I was
yeah.
saying, oh boy, dual cone. You gotta have a second cone. Well, one cone where they spend a lot of money, and they really have a lot of money. I said, okay, can we do this with just one cone? This is like one laser. And I was thinking about it, and yeah, it just came to me. Yeah. But somebody thought about the same idea. And they published a paper a little.
Well, it's great. It's great. I love to see the activity here. The students, the group getting into this area. I think is a very good choice of area. I hope we can ramp up our research. We got a patent awarded recently for distributing the energy in space, which we hope we can build into this kind of approach. But anyway, I would say to the students who are here at UAH, good for you for being here. Tom, if you would like me to talk about what we're working on, it doesn't have to be right away, but I'm available.
Okay, great.
Okay.
Always have to have speakers lined up.
Yes, sir.
Well, let's turn our